Welcome back, learners. Now moving on to this next set of questions, being the application questions, we need to begin. And the first question is asking us to convert the following masses to kilograms. So remember that the SI unit for mass must always be kilograms. Whatever unit of mass we are given, it must always be converted to kilograms, the kgs. So now, we are given 350 grams, 5 grams, 60 grams, and 2,500 grams. So when we are moving or converting from grams to kilograms, remember we are supposed to divide by 1,000. That then means when we are converting the 350 grams to kilograms, you're going to divide the 350 by 1,000. And that is going to give us, our 0.35 kilograms. So when dividing the 350 by 1,000, we are getting 0.35 kilograms. And then with the 5 grams, again we're going to say 5 divided by 1,000. This is going to give us 0.005. And this is going to be our kilograms. Next question, we are supposed to convert again 60 grams into kilograms. Again, we are dividing 60 by 1,000, and dividing 60 by 1,000 will be giving us 0.06. 0.06. That is going to be our 60 grams. And remember, must be in kgs if it's 0.06. And then the last one, dividing 2,500 by 1,000. So it's 2,500 divided by 1,000. And that is going to be giving us 2.5 kilograms. So we've converted now all our grams into kilograms by making use of this rule that when we are moving from grams to kilograms, we're dividing by 1,000. But when we are moving now from kilograms to grams, we're supposed to multiply by 1,000. Always need to remember that. Now, question 2. Question is now, what is meant by the weight of an object? So we do know that mass is the amount of matter making up a substance or making up a body. Now with the weight is mass multiplied by acceleration due to gravity. So in simple terms, W for weight is equals to mg, mass multiplied by the acceleration due to gravity. Now on Earth, this acceleration due to gravity is equals to 9.8. It is equals to 9.8. And this is only unique to Earth. If you were to go to a different planet or go to the moon or go anywhere else but then outside of Earth, then that acceleration due to gravity is going to be different. It can either be smaller, it can be greater, depending on where you are. But on Earth, what we have, it is going to be 9.8. So, because weight is a force, and that force is always acting downwards, because we're saying that everything that goes up must come down because of the weight. And remember that is now going to be the gravitational force that is being applied onto the object that is somewhere mid-air and pulling it back to the Earth's surface. So because it is a force, then the unit, the SI unit for weight is going to be Newton, which is capital letter N. So we're measuring any force in newtons, be it weight, be it gravitational force, be it magnetic force, or any other force. A force is always measured in newtons. Next question. So question 4 is asking us, how can the weight of an object on Earth or another planet be calculated? So we need to know how to calculate the weight of an object if it's here on Earth or in a different planet. So for us to be able to do that, we need the following. Weight is now going to be mass multiplied by the gravitational acceleration. So for us to be able to calculate the weight of an object, we need the object's mass and the gravitational acceleration of that particular planet, either here on Earth or any other planet. So this is how we're going to calculate the weight of that object. Now remember that weight is a force and it is measured in newtons. So whatever answer that you get must always be measured in newtons, or have the units newtons. Now question 5. Is the weight of an object the same everywhere in the universe? And we need to explain why we are saying that. So first of all, the weight of an object depends on where it is in the universe. So which then means it is not the same. That means it is not the same. So the first answer there, it is going to be no. So the weight of an object depends on where it is in the universe. If it is here on Earth, it will have a different weight. And the very same object with the very same mass, take it to a different planet that has a different gravitational acceleration, then the weight of that object in that planet is going to be different. It can either be higher or it can be lower than the weight of that object on Earth, depending on the gravitational acceleration. For instance, if we were to take an object that has a mass of 10 kilograms, this is now Earth. We're talking about Earth now. Let's just say Earth. This object has a mass of 10 kilograms. And we know that our gravitational acceleration here on Earth, it is 9.8 meters per second squared. Which then means for us to determine the weight of this object, we're going to use this main equation as we have discussed. W is equals to mg. So that means W is equals to the m10, which is our mass, and then the gravitational acceleration is going to be 9.8. So when we are multiplying these two numbers, 10 times 9.8, we are getting 98 newtons. So the weight of this object here on Earth will be 98. But take the very same object with the very same mass into a different planet. Now, assuming that that planet has a mass or has a gravitational acceleration of 5. So that means the mass on a different planet, so a hypothetical planet, the mass on that planet is still 10 kilograms. But the gravitational acceleration now we said is 5 meters per second squared. So which then means your weight, or the weight of this object there, will be 10 for the mass. Remember, we're using this equation. 10 for the mass multiplied by the 5 for the gravitational acceleration. This is your g. Which then means the weight of this object on that hypothetical planet is going to be 50 newtons. So as you can see, the weight of this same object, same mass, same everything, on planet Earth, it has a weight of 98 newtons, but on this different planet, it has a weight of 50 newtons. So therefore, the weight of an object is not the same anywhere in the universe. That weight depends, so to answer the last part, it depends on gravity. As we have seen, it depends on this little thing here, on our body here, the 9.8 or the 5 or whatever number that you have, depending on where you are. Then question 6 is asking us that, is the mass of an object the same everywhere in the universe? And we need to explain. So if we were to take this object from planet to planet, or from Earth to the sun, to the moon, to anywhere, the amount of matter making up that particular object will remain the same. Nothing is going to change. So the mass of an object remains the same everywhere. Yes, the mass of an object is the same everywhere. Why? Because the amount of matter doesn't change or will not change. the amount of matter making up that object is not going to change. What is going to change is going to be the weight of this object depending on where it is in the universe. Now, the next question says now, which one of the following statements is false? So out of the 4 statements that we have, we need to identify the one that is false. The statement number 1 says, in order for a non-moving object to start moving, a net force must act on it. So if a stationary object is just stationary there, if I now start to push it or to pull it, then that object is going to move. If we have a stationary object, it's stationary, it's not moving. When I push it or when I pull it, it will start to move. So therefore, this is true. Contact forces are strongest when the objects experiencing the force are touching. Remember, contact forces, that's now between 2 objects, and those 2 objects are supposed to be in contact or touching each other. So this statement, it is also true. Field forces act over a distance, but they can also act when objects are touching. And the last one says, forces always act in pairs of equal strength, but these pairs act on different objects. So we know that field forces or non-contact forces, they act over a distance, right? So there's a force of attraction that is acting over a distance. But that force of attraction can still act even though the 2 objects are in contact or they are touching each other. So statement C is also true, which then means statement D is false, because forces always act in pairs, that is true. Forces always acting in pairs of equal strength, but these pairs act on different objects. So the forces are supposed to be acting on the same object, because forces always act in pairs. If you're applying a force into an object, that object will simultaneously exert the same force back to you, so the object are always acting in that same object, or the forces are always acting in that object. Next question. Which one of the following is not a field force? Remember, field forces, forces acting at a distance, non-contact forces. Gravitational force, that's a field force because that's now a force between, we can say, an Earth and the next planet, which is Mercury or any other planet. They're applying a force onto each other. And then a frictional force, that's now a force between the surface and the object that is in contact with. So now it draws this one out. And an electrostatic force, that's now a force between 2 charged particles, either a positive and a positive, or a negative and a positive, or a negative and a negative. Those particles or those electrons and protons, they are not touching each other. They are just exerting an electrostatic force between them. So that's also a field force. And a magnetic force, again, it's a force that is a magnet exerts on the other object over a distance. So this is also a field force. But a frictional force, it is that force that is acting between 2 objects that are in contact with each other. And our last question says, the correct unit for gravitational force is, remember, keyword there is force. So force is measured in newtons, which is capital letter N. And therefore our answer is A, because kilograms, that's now the measure of mass, right? And this is newtons per kg, and this is kilogram per newton. So none of these are measuring force, and the only one that measures force or unit of measure for force is Newton, which is denoted by the capital letter N. So before moving on to the next part, we are just going to quickly go for a short break, and I will see you just after this.